Now, if we compare these numbers with the numbers that we can see on the table, you should discover how these numbers correlate with one of the columns on this table. And hopefully you paused and looked and found that the column is the average altitude column. Now, we've rounded these numbers off. If they'd been expressed exactly, they would have come out exact. And they would have been exactly the same as the average altitudes. You can see that these numbers are the rounded values of the average altitudes. So that the average slopes of the accumulated area graph are the altitudes of the original graph. Now, that's actually nothing too astonishing if you think about where we got these numbers. And you, without looking at what I've done, you ought to try to figure out why that happened. How were these altitudes here calculated, these values of the accumulated area, and how could that be related back when we find the slopes of this graph to these quantities? It's not very deep, okay, but it's a very deep and important result when you come out down to it. Okay, well, here's the reason. A slope of the accumulated area graph is the change between two of these values, for example, between 0.617 and 1.27 here. Okay, that's the change in the accumulated area from the original graph. But how did we get the change in the accumulated area? We got the 1.27 from the 0.617 here by adding the area of this second trapezoid. And you want to think deeply about that and make sure you understand how that gave us the difference between this and this. So that the slope of the accumulated area graph between here and here is just the change in the accumulated area divided by the width. And of course, that's no surprise because these are accumulated areas. We take the change in these quantities and divide by the width. But that's equal to the area of the original trapezoid on the original graph, because to get this accumulated area, we added this to this accumulated area. This is just the area of this trapezoid. So it's the area of the original trapezoid divided by its width. So that this slope here should be the area of this trapezoid divided by its width. Well, that's clearly the case. If we divide 0.653 by 0.1, we get 6.53. Now, why did that happen? How did we calculate the area of this trapezoid? We took the average altitude and multiplied it by the width. So the area of the original trapezoid is its average altitude, the average altitude of the original trapezoid multiplied by the width. And we're dividing that by the width. So what do we have left? We have the average altitude of the original trapezoid. So the slope of the accumulated area graph represents the average altitude of the original trapezoid. So our accumulated area function, which has values 0.617, 1.27 up to 3.51, is our change in antiderivative function, which is, of course, a definite integral. Okay, our antiderivative function for the function y equals x cubed plus 5 is y equals x to the 4th over 4 plus 5x. The value of our antiderivative function at t, we don't want to use x, we're going to use t because I want to relate this to an integral and notation and so forth. There's no really good way to do this without a little confusion. But we're going to say that the value of our antiderivative at t is t to the 4th over 4 plus 5t. The value of our antiderivative at 1 is, well, evaluate the antiderivative function for 1. X to the 4th over 4 plus 5x becomes 1 to the 4th over 4 plus 5 times 1. Just like our antiderivative function at t is t to the 4th over 4 plus 5t. The difference in those two functions, the change in our antiderivative, is then the y equals, or the t equals 1 value, or the x equals 1 value, it doesn't matter. The value at 1 subtracted from the value at t, which gives us t to the 4th over 4 plus 5t minus 5.25. So this is the change in our antiderivative from x equals 1 up to x equals t, where t could be any one of these x values here, okay, or any x value if we want to extend this table. The change in the antiderivative function is, of course, equal to the definite integral. So that's why I invoke the idea of definite integral. The integral from 1 to t of y of x dx is, again, just t to the 4th over 4 plus 5t minus this quantity here where we substitute 1, and we get this value again. If we evaluate this function for t equals 1, 1.1, 1.2 up through 1.5, we are going to get these values, or more accurately, the values on our accumulated area table here. So these values do represent the change in antiderivative values. That is, the values of the definite integral of our original function, the values that show up on our table of accumulated areas, and the values on this accumulated area graph, so that this is a graph of this function. With each of these values representing the change in area of our original function, starting at x equals 1 up to whatever our value of t might be. Okay? So you will have a much better understanding of the integral and the things that you learned in calculus, if you learned these things in calculus, and a much deeper appreciation of what these quantities, these graphs, and what integrals are telling you. We have again seen that the slopes of the accumulated area graph are equal to the values of our original function, at least the average values of our original function on each interval. As the intervals shrink down, the differences between the average altitudes and the actual altitudes also shrink down. So in the limit, our average altitudes become the values of our functions. So that we can state, since our slopes are average values of our derivative, with a little bit of work related to limits, this illustrates how the derivative of our antiderivative function is equal to our original function, which is the fundamental theorem of calculus. And the reason that's the case just really goes back to this argument here. The slope of our accumulated area graph is, in a very simple manner, demonstrated to be equal to the average altitude of the original trapezoid, so that if we have an accumulated area function, its derivative has to be equal to the original function.